Top 20 Electronics Interview Questions and Answers. Explore the top 20 electronics interview questions and answers, covering microprocessors, Ohm's law, logic gates, transistors, and more, offering practical insights for enthusiasts and professionals in electronics and circuit design. 1. What is the difference between a microprocessor and a microcontroller? A microprocessor is a central processing unit, CPU, on a single chip, designed to execute instructions from programs by performing fetch, decode, and execute cycles. It requires external components like RAM, ROM, and peripherals for operation. A microcontroller, however, integrates a CPU, memory, RAM, ROM, and peripherals, e.g. timers, I/O ports, on a single chip, making it self-contained for embedded applications. Microprocessors excel in computing power, while microcontrollers are optimized for specific low-power tasks. 2. Explain Ohm's law and how it is used in circuit design. Ohm's law states that voltage V across a resistor equals the product of current I and resistance, R V equals I times R. In circuit design, it's used to calculate appropriate resistor values to limit current, ensure proper voltage drops, or protect components. For example, selecting a resistor to limit LED current prevents damage. It also aids in analyzing circuit behavior, ensuring components operate within safe limits, and designing voltage dividers or current paths in complex circuits. 3. What are the different types of logic gates and their truth tables? Logic gates include and or not, NAND, NOR, XOR, and XNOR. An output's true if all inputs are true, or if any input is true. Not inverts the input. NAND and NOR are inverted and or. XOR is true for odd true inputs. XNOR for even. Truth tables list all input combinations and corresponding outputs, e.g. and 000, 010, 100, 111. These gates form the basis of digital circuits, enabling computation and decision-making. 4. How does a transistor work, and what are its common configurations? A transistor is a semiconductor device that amplifies or switches electrical signals. In an NPN bipolar transistor, a small base current controls a larger collector-emitter current. In MOSFETs, a gate voltage controls current between source and drain. Common configurations are common emitter, amplification, high gain, common collector, voltage follower, high input impedance, and common base, high-frequency applications. Transistors are used in amplifiers, switches, and digital circuits, enabling signal processing and logic operations. 5. What is the difference between analog and digital signals? Analog signals are continuous, varying smoothly over time, e.g., audio waveforms, representing infinite values within a range. Digital signals are discrete, represented by binary values, zeros and ones, typically in square waves. Analog signals are susceptible to noise, requiring precise amplification, while digital signals are robust, easily processed by logic circuits. In electronics, analog is used in sensors and audio, while digital is used in computing and communication for reliable data transmission. 6. Can you explain the working principle of an operational amplifier, op-amp? An operational amplifier, op-amp, is a high-gain voltage amplifier with differential inputs, inverting and non-inverting, and a single output. It amplifies the voltage difference between inputs, ideally with infinite gain, high input impedance, G-stand low output impedance. In negative feedback configurations, e.g., inverting or non-inverting amplifiers, the output stabilizes to maintain input voltage equality. Op-amps are used in amplifiers, filters, oscillators, and signal conditioning, enabling precise control in analog circuits. 7. What is a filter circuit? Describe the difference between low-pass and high-pass filters. A filter circuit selectively allows certain frequency components of a signal to pass while attenuating others. Low-pass filters allow frequencies below a cutoff frequency to pass, attenuating higher frequencies, e.g., used in audio to remove high-frequency noise. High-pass filters allow frequencies above the cutoff to pass, attenuating lower ones, e.g., used in radio circuits to block DC. Both use capacitors, inductors, or resistors, with cutoff frequency determined by component values. 8. What are the common types of diodes and their applications? Common diodes include 1. Rectifier diodes, convert AC to DC in power supplies. 2. Zener diodes, regulate voltage by conducting in reverse bias at a specific voltage. 3. Schottky diodes, fast switching, low voltage drop, used in high-frequency circuits. 4. LEDs, emit light, used in displays. 5. Photodiodes, generate current from light, used in sensors. Diodes control current flow, protect circuits, or enable specific functions like rectification or light emission. 9. Explain the concept of impedance in AC circuits. Impedance, Z, in AC circuits is the total opposition to current flow, combining resistance, R, and reactance, X. Where Z equals R plus JX, J is the imaginary unit. Reactance arises from capacitors, decreasing with frequency, and inductors, increasing with frequency. Impedance, measured in ohms, affects current amplitude and phase in AC circuits. It's used to design filters, match circuits and amplifiers, and analyze signal behavior in complex AC systems. 10. What is PWM, pulse width modulation, and where is it used? Pulse width modulation, PWM, is a technique where a digital signal's duty cycle, on-time percentage, is varied to control power delivery while maintaining a constant frequency. It effectively simulates analog control, adjusting average voltage. PWM is used in motor speed control, e.g., in drones, LED dimming, power supplies, e.g., voltage regulation, and audio signal modulation. Its efficiency in controlling power without significant heat loss makes it ideal for embedded systems and energy management. 11. How would you troubleshoot a non-working circuit board? To troubleshoot a circuit board, first visually inspect for physical damage, loose connections, or burnt components. Check power supply voltages with a multimeter. Verify continuity in traces and solder joints. Test components, resistors, capacitors, ICs, using a multimeter or oscilloscope. Use a schematic to trace signal paths, checking for expected voltages or signals. Isolate faulty sections by dividing the circuit and replace defective components. Document findings to avoid repeated issues and ensure systematic debugging. 12. What tools and instruments do you commonly use in electronics labs? Common electronics lab tools include multimeters, measure voltage, current, resistance, oscilloscopes, analyze waveforms, function generators, produce test signals, power supplies, provide controlled voltage current, soldering irons, assemble circuits, and logic analyzers, debug digital signals. Additional tools include breadboards, wire cutters, tweezers, and desoldering pumps for prototyping and repair. Software like LTSpice or KiCad aids simulation and PCB design. These tools enable circuit building, testing, and troubleshooting across analog and digital applications. 13. Describe how to use an oscilloscope to analyze a waveform. To analyze a waveform with an oscilloscope, connect the probe to the circuit point, ensuring proper grounding. Set the voltage scale, volts diV, to match signal amplitude and the time scale, times diV, to capture the waveform's period. Adjust the trigger level to stabilize the display. Observe the waveform's shape, amplitude, frequency, and phase. Measure parameters like peak voltage or period using cursors or auto-measure functions. This helps diagnose signal integrity, noise, or timing issues in circuits. 13. Have you ever designed or built a PCB? What tools did you use? While I haven't physically built a PCB, I can describe the process. PCB design involves creating a schematic, selecting components, and laying out traces using software like KiCad, Eagle, or Altium Designer. Tools like a soldering iron, reflow oven, or pick-and-place machines are used for assembly. Gerber files are generated for manufacturing. Testing tools like multimeters or oscilloscopes verify functionality. These tools ensure precise design, component placement, and reliable circuit performance. 15. What are common causes of component failure in a circuit? Component failure in circuits often results from overvoltage, exceeding component ratings, overcurrent, causing overheating, thermal stress, prolonged high temperatures, mechanical stress, vibration or physical damage, or manufacturing defects, e.g., poor soldering. Electrolytic capacitors may fail due to aging or leakage. ESD, electrostatic discharge, can damage sensitive ICs. Incorrect polarity or improper handling during assembly also contributes. Environmental factors like humidity or corrosion can degrade components, necessitating proper design and protection measures. 16. Describe a project where you faced a technical challenge and how you overcame it. In a hypothetical Arduino-based sensor project, I faced inaccurate temperature readings due to noise. The challenge was traced to interference in the analog sensor signal. I overcame it by adding a low-pass filter to remove high-frequency noise, improving signal quality. I also shielded the sensor wiring and used a stable power supply. Testing with an oscilloscope confirmed cleaner signals, and recalibrating the sensor resolved the issue, ensuring accurate data for the project. 17. Have you worked in a team on an electronics project? What was your role? In a simulated team project for a robotic arm, I acted as the circuit designer. My role involved creating the schematic, selecting components like microcontrollers and motor drivers, and designing the PCB layout using KiCad. I collaborated with programmers to ensure hardware-software compatibility and with mechanical engineers for integration. Regular team meetings ensured alignment. My contribution ensured reliable power delivery and signal integrity, enabling the ARM's precise control and successful project completion. 18. Tell me about a time you had to debug a complex issue in a circuit. In a hypothetical audio amplifier circuit, distorted output was the issue. I used an oscilloscope to observe clipped waveforms, indicating overdriven transistors. Checking the schematic, I found incorrect biasing resistors. Using a multimeter, I verified voltages, confirming the error. I recalculated and replaced the resistors to set proper bias points. Testing again showed clean output. This systematic approach, visual inspection, signal analysis, and component verification, resolved the distortion, ensuring the amplifier met performance specifications. 19. How do you keep your electronics knowledge up to date? Staying updated involves studying recent advancements through online resources like IEEE journals, electronics blogs, and posts from industry experts. I explore tutorials on platforms like Coursera or YouTube for emerging technologies. Engaging in forums like Stack Exchange and experimenting with tools like LTSpice or Arduino keeps skills sharp. Attending webinars or virtual conferences on topics like IoT or power electronics also helps. Continuous learning and hands-on practice ensure my knowledge aligns with current trends. 20. What electronics project are you most proud of and why? I'm proud of a hypothetical IoT-based home automation system I designed. It integrated sensors, a microcontroller, and Wi-Fi for remote control of lights and appliances. The challenge was ensuring reliable communication and low power consumption. Using MQTT protocols and efficient coding, I achieved seamless operation. The project's success in providing user-friendly control and energy savings was rewarding. Its real-world applicability and integration of hardware/software skills made it a standout achievement in my portfolio. Mastering these electronics interview questions not only prepares you for technical discussions but also boosts your confidence in real-world problem-solving. Whether you're a fresher or an experienced professional, deep understanding is key to standing out. Ready to take the next step? Start practicing your answers, build mini-projects, and stay curious. If you need mock interview support or detailed answer guides, reach out now and level up your electronics career.